All right, so chapter 3, we were looking at two variable statistics, specifically two quantitative variables. All right, two quantitative variable statistics. R is the correlation. This tells the strength and direction. If it's closer to 1 or -1, it is stronger. If it's closer to 0, it is weaker. So R has to be in between -1 and +1. +1 would be a perfect positive correlation. -1 would also be very strong. This would be a perfect negative correlation. The closer we are to 0, the weaker the correlation. Outliers are any points that don't follow the pattern. With an influential point, removing the point would greatly affect the correlation or the least squares regression line. And then high leverage has a very high or very low X value. The high leverage points are the ones where we think of this like a teeter-totter. And if you put weight on one side, what's going to happen to the overall line? Those would be those high leverage points. When we interpret the scatter plot, we have Duff's, direction, unusual points in context, form, and strength. Residual, A minus P, actual minus predicted. If we have residual that is greater than 0, actual minus predicted is greater than 0, then our actual is bigger. And so the model underestimates. If the actual is bigger, the model underestimates. If the residual is less than 0, actual minus predicted is smaller than 0, so that means the predicted is bigger. Then the model is overestimating. There's a couple other things I want to say about R, but I don't have a lot of room to write it down here. We're going to write it down on the next page so that we have some room for that. When the residual plot shows no distinct pattern, then a linear model is appropriate. We are still on the front side. There's just more room to write on the back for when we get back there. You're going to use linreg a plus bx to find the slope and the y-intercept when given data. You will put the data in a table before you try to run linreg. linreg is a linear regression. It will find the least squares regression line. When we are given statistics, we can find the slope and the y-intercept, A and B, by using these formulas. This is the mean of y, and this is the mean of x. To find B, we would have to find B first and then substitute it into the y bar equals A plus B times x bar formula. In order to use that, we have to know the standard deviation of y. We have to know the standard deviation of x. And we have to know R, the correlation. That will allow us to find the slope. So again, we use this to find slope and y-intercept. Association does not imply causation. Other factors might be the cause. We can have confounding variables. What do we have to have if we're going to show cause? Not just a random sample. Random sample lets me generalize to my population. Random assignment experiment, yes. Must have a randomized experiment. To show cause. Right. So then we've got some examples of interpreting in context. using our Duffs. When we describe the correlation, when we interpret the correlation, we talk about the linear association. Correlation always tells me how good a line will fit the data. Not any other shape, it's always how good a line fits. The association between X and Y context is, it can tell us whether it's weak, moderate, strong, and it can tell us whether it's positive or negative. Those are the only things R can tell us about. It does not tell us whether or not a linear model is appropriate. It just tells us how well the data fits a line, if that makes any sense. To determine whether a linear model is the best fit, we would need to look at a residual plot, because we would be looking for that curved pattern on the residual plot to say, no, a linear model is not appropriate here. The residual, we would say the actual Y context was whatever our residual is, above or below the predicted value when X is whatever. So the example that we have there, the actual heart rate was 4.5 beats per minute above the number predicted when Matt ran for 5 minutes. When we interpret the y-intercept, we always talk about the predicted. Don't forget that predicted word there, super important. Remember, this is the chapter where we talk about predictions. We're not ever going to have just a y equals. This is always our y hat equals. I know we've looked at that formula just a little bit ago that was the y bar. That's when we're trying to find slope and y-intercept. The predicted y context when x equals 0 in context. Sometimes it doesn't make any sense to say 0, and so we'll just look at another way of describing that. Sometimes none is a better way of describing that. So like you would never say somebody is 0 years old necessarily, because that doesn't necessarily make sense, but you can say that they're a newborn. So sometimes it doesn't make sense to use the word 0 in there. But it's still the idea that x is 0. Slope. For each additional x in context, it's always for every one more x. And I actually want you guys to add those words in there. For every additional one more, whatever our x context is. And this is where I'll flip the page. The predicted y in context increases or decreases by whatever the slope is. One of the biggest things that I saw happen on the Module 12B test, where we kind of revisited some of these concepts and we interpreted y-intercept and slope in context, I was seeing that you would say for every one more y, the x is predicted to go up or down. Make sure that you've identified which is your x and which is your y. It's always for every one more x. The denominator on the slope would be a 1, and it's rise over run. Y over x. So for every one more x, what is the y predicted to do? Standard deviation of the residuals, that is our S. We talked about that in chapter 12b. The actual y context is typically about S away from the value predicted by the least squares regression line. And then we had our coefficient of determination, our R squared. I have seen this one show up a lot on free response questions. They'll ask you to interpret R squared in context. When we interpret R squared in context, it's telling us the percent of the variation. How much of the change that we see in Y is because of the linear relationship that we see in X, or with X. Think of it this way. Anybody in here have a job? If you work more hours, what happens to your paycheck? Goes up. If you work less hours, goes down. Do taxes affect that at all? Yes. Most of the change that you see in your paycheck, most of the change in Y, in the output, is because you worked more or less hours. That's what R squared is telling us. How much of the change in your paycheck is because of the difference in number of hours that you worked? Does that make sense? Okay. All right, we've got some space down here, about 2/3 of the page. We're going to add some additional notes here. Thank you. You can just put it on my desk. All right. When we describe scatter plots, and we use Duff's. Oops, I did not want to use the highlighter. Things that you want to make sure to hit on. The D, that is your direction. The only thing we'd be looking for here is a positive or negative based on what the slope is. As you move from left to right across the horizontal axis, do the dots tend to go up or do the dots tend to go down? U, this is our unusual features. Notice we didn't say outliers. It includes outliers, but it also includes other things. Unusual features would be things like clusters. Is there like two big clusters of data? Are there gaps? And then also, are there outliers? Basically, is there anything that is outside of the pattern? Is there anything that is noticeably outside of the pattern? F is for form. When we are describing a scatter plot, we will describe it as a linear association unless it clearly has another pattern. If you had a scatter plot that looked like this, I would not describe that as a linear form. But if I have a cluster of dots that just kind of looks like a cloud shape, it doesn't have a strong U shape, it doesn't have a strong J shape, I'm going to describe it as a linear association. We would have a line of best fit to model that data. And then the S is for strength. So ways that you would do strength. When we just looked at this on the other page, it said weak, moderate, or strong. I personally have seen a lot of pushback when we just say moderate. We'd want to say like moderately weak or moderately strong. Which way is it tending? So weak, moderately weak, moderately strong, or strong. If you have regression data to look at, if you have the little box where it gives you the slope and the y-intercept, and we saw it also gives you t and p when we were doing inference with slopes. If you have that and you have access to r or r squared, you can use r to help you as you're describing the strength of this. Anything between 0 and 0.5, I would probably describe as weak. Anything between 0 and negative 0.5, I would also describe as weak. As we start to get bigger than 0.5 and smaller than negative 0.5, we're going to be strengthening from there. So moderately weak, moderately strong, or strong. The closer we get to 1 and negative 1, the stronger our association is. All right. Some R stuff now. Correlation. Or R. R has no units. Changing units on x and y does not change r. Ooh. Both variables have to be quantitative. I mentioned this already, but R does not tell you if a linear model is best. You need the scatter plot and or the residual plot for that. R is the same if you flip x and y. The explanatory and response. One more thing that I want to add, I don't have any room at the bottom. Hopefully you still have a little bit of room at the bottom. One thing that I wanted to write here though, y hat oh my goodness, I can't draw a hat to save my life right now. There we go. Y hat equals A plus BX. Right here for A, X always equals 0. That's our y-intercept. Thank you. B, our slope. This is the change in y divided by the change in x. And the change in x will always be equal to 1. We always have one more x, and then how is the y adjusting because of that? And this hat up here means what again? Predicted. Super important whenever we are describing the y-intercept of the least squares regression line, the slope of the least squares regression line, or any predictions that we make using the least squares regression line, that we always address the fact that these are predictions. These are not actual observed values. These are all predictions. All right. Let's see what we can do. Bivariate data. What does bivariate mean? Two variables. Bivariate, two variables. Bi meaning two, and then variate, just a shortening of that word variables. So two variable data. Explanatory variables, we attempt to explain the observed outcome based on, or that this is our independent variable. We think this will explain the output that we're seeing. And then our response variable, this is the measure of the outcome of the study. This is our dependent variable because it depends on what x is. I want to look at this scatter plot on the right. Which of those 2 points, A or B, would make the most sense to remove if we could? A. Why? Yeah. Even though most of my data is in the upper left, if I draw in that line of best fit, B is following that pattern. A is not following the pattern. A is an outlier. B is an influential point, but not an outlier. Do the points have a positive or negative association? Negative, because they're all going down. We have a negative slope. Yeah. Do you guys remember what least squares means? It's been a hot minute since we've touched on this. The squares of the residuals, the least squares regression line means that we have the smallest sum of the squared residuals for all of the data points that we have. The sum of the squared residuals is the smallest possible. All right. Somewhere in a margin, you're welcome to grab a whiteboard if you want to, but this isn't really whiteboard worthy necessarily. I want you guys to calculate the residual using this least squares regression line, which technically speaking, we should have a hat over our y if it's a least squares regression line. This is the actual point. I would like for you guys to calculate the residual. So in a margin, or you're welcome to come up and get a whiteboard if you want to. Or just in a margin on your page. How do you calculate a residual again? Residual equals actual minus predicted. So what would the actual be here? 19.5, because we're always looking at the output when we subtract to get our residual. 19.5 minus, does anybody have a predicted amount? 23.9. And so when you subtract those, you get what? Negative 4.4. There's our residual. So if I were looking at a scatter plot with all of this data, would this point right here lie above or below our linear regression line? Below. The actual is smaller than the predicted, so the point is going to lie below the line. So does that mean the model is over-predicting or under-predicting? Over-predicting. The line is above the point, so you would have to go up to get to the predicted. So that means it's an overestimate. If the point is above the line, you would have to go down to get to the predicted. That means it's an underestimate. So the positive or negative on the residual tells you where this point lies in relationship to the line of best fit. But as far as whether it's an overestimate or an underestimate, it feels kind of backwards based on the sign that you get for your residual. Because it's which direction would you have to move to get to the line, to get to the predicted? Would you have to move down, therefore it's an underestimate, or would you have to move up, therefore it's an overestimate? Does that make sense? Okay. What to do if you are given a set of quantitative bivariate data? Make a scatter plot and look at it. How do you do that? Do you guys remember how to do that on the graphing calculator? So you'd start by putting your data into the table, into the lists, and then you would hit the second and y equals so that you can look at the different types of graphs. I'm pretty sure it's second and y equals. I'm not looking at a calculator right now. Yes, second and y equals takes you to all the different types of statistical plots. You can choose a scatter plot. It's one of the first options available there. You want to make sure that it's flashing and darkened around the scatter plot. You want to make sure that it knows where it's pulling the x data and the y data from. You have to tell it list 1 and list 2. And then we're going to do the zoom and stat. So you push the zoom button, it's just 2 over from the y equals. And option number 9 there is zoom stat. That will resize the window. It's not perfect, but it's better than just going to the graph itself, where sometimes it's not centered correctly for your data. You can be more precise and change the window by hand if you want to, but zoom stat usually is good enough for us to look at that data. Finding a linear regression equation. How do you do that? This is where we have to do the lin reg. A equals bx. And lin reg is not that. Wait, stat calc. And then lin reg is option number 8. We want the a plus bx. We want y-intercept first and slope second. I know that's backwards from Algebra 1 and Algebra 2 and every other math class you've ever taken. But in statistics, we like the y-intercept first and the slope second. The best explanation that I've heard for that is because when you write a linear regression equation, it is standard practice to not use x and y, but to actually put the variable names in there. And so if we do the slope with the x next to it, we have room to write out that entire variable name, as opposed to writing the slope, the variable name that might be 2 or 3 words long, and then a plus or minus our number, and it gets lost in there. It's the best explanation I've heard. I'm sure it's not the only one, but that's the best one that I've heard. Making a residual plot. This we can do on the graphing calculator, and I'm happy to show you as we get closer to the test how to make the residual plot using your graphing calculator so that you can check to see whether or not a linear model is appropriate. If the regression equation has a pattern, if your residual plot has a pattern to it, you can try to straighten the curve using a transformation, using a quadratic transformation, an exponential transformation, or a logarithmic transformation. These are the types of things that I would expect to show up in multiple choice questions or on the exploratory task, which is question number 6. It's always going to be that last question in the FRQ. It's got more parts. They tell you to set aside a good chunk of time for question 6 by itself. They might ask you to do stuff like this, but there's also going to be some more scaffolding to it there. But I would not expect this to just show up in the regular FRQs. All right. If the linear regression equation to find the temperature on the top of Flat Top Mountain is based on the temperature, of Denver is, and then here's our regression equation, y hat equals 1.2x minus 31, where x is Denver's temperature and y is the temperature on the top of Flat Top Mountain. Describe what the coefficients mean. What does this 1.2 mean here? What is it? That's the slope. So now I want you guys to practice. You can do it in your head. You can jot it down on paper. You can come get a whiteboard. I want you to put that into words, how you would describe or interpret the slope. You can look at the page in your yellow packet, too, for an interpretation of slope or help with an interpretation of slope. going to give you guys a couple of minutes. I want you to do that for both the 1.2 and the negative 31. And then I want you to do the bottom two pieces and interpret r and r squared. So I'm going to give you guys a couple minutes to do all four components here. Yes. You're welcome. All right. If you're still working on these, that's okay, but I'm going to start to go through them. And as I reveal the answers, this is all coming from this printed packet that I got from somewhere else, so we're going to kind of modify the answers a little bit. I want you guys to help me pick out the things that I would have different about this answer so that you get full credit. So the 1.2 means that for every degree the temperature goes up in Denver, the temperature rises 1.2 degrees on top of the mountain. I see two things that I would either add or change. For every 1 degree, I would be really explicit about that. I would always write for every 1 more whatever our x is. I've just seen too many times where it's kind of on the fence, and then when they get to the end of the question and they're scoring the whole thing, they end up rounding it down rather than rounding it up based on the quality of the explanation. So adding that 1 more would be very clear communication. And there's one other thing that's missing here. Predicted. I would have the predicted temperature, not just the temperature. Negative 31 means that when the temperature in Denver is 0, the temperature on the top of Flat Top Mountain is 31 degrees below, or negative 31 on average. I would still put the word predicted in here, but that on average kind of takes care of that piece. We're not saying it's exactly this. We're saying it's about this. So I would still put in predicted here. What does it mean if R is 0.87. Strong and positive. That's what we can tell from R. There's a positive linear correlation between the two temperatures. I would even say strong. Positive linear correlation. I would make sure to get this word in there as well, that linear, because again, R tells us how well does a line fit the data, not whether or not a line is the best, but how well does a line fit. And then R squared, 0.7569. What's that telling us? 79.65% of the variation in temperature on Flat Top Mountain. Why? 75.69% of the change in Y, the change in temperature on Flat Top Mountain, is because of what? Yes, because of the relationship with variation in temperature in Denver. I would even say is accounted for by the linear relationship. So I would say is accounted for or because of by the linear relationship with temperature in Denver. That's the way I would word this. I would work really hard to try to get yourself to remember that paycheck versus hours worked as you're describing R squared, to remember how to interpret that. This percent of the change in your paycheck is because of the difference in number of hours that you worked. It's because of the linear relationship, because of the rate of change that you get, your pay, your hourly pay. All right. A couple of notes to make. Making predictions using the regression equation may not be useful outside of the range of the data. It often doesn't make sense. This is called extrapolation. So we can use our least squares regression line to make predictions that are within the set of data that we have collected. But outside of that set of data, things that are, have X values way, way smaller or X values way, way bigger, it might not follow the same linear pattern that far out, that far away from our data. It might behave in a linear way close to the data that we're looking at, but not behave in a linear way further out. Just because two things are associated doesn't mean one causes the other. There may be a lurking variable that has an effect on both. This is called confounding. In order to determine causation, you have to have an experiment. We chatted about that already. This note right here. If we have two or more categorical variables, we don't do scatter plots for categorical variables. That's when we did our chi-square testing. That was the first part of chapter 12. In that case, we calculated the percents, the distributions, and we tried to see if the distributions matched a given distribution. That was the test for goodness of fit. Do two distributions match each other? That was homogeneity. And are these two variables related? Do they have an association? Is there a linear relationship here? Or not linear necessarily, because we're not talking scatter plots, but is there a relationship between these two things? All right. You guys okay if we look at some FRQs now? Right. You are probably going to want a whiteboard for this. So if you didn't grab one earlier, please come and grab a whiteboard. You guys see those words okay, or do I need to kind of zoom in? Can you make them out? I know it's kind of small from the back. Yeah, I can zoom in a little bit. I'll zoom in so you can see the top part, and then I'll zoom in so that you can see the questions at the bottom. All right, so there's the question prompt, a little bit bigger. You can read that and look at the scatter plot with the least squares regression line. I'll give everybody a couple of minutes to read, well, like a minute, minute and a half to read this, and then I'll scroll down so you can see the questions. You guys okay if I scroll down? You can still see the scatter plot, and then there's A, B, and C down at the bottom. So part A, identify the intercept and interpret it in context. B, identify R squared and interpret it in context. And then C, you won't be able to circle it on the scatter plot since it's only projected, but you should be able to identify what the outlier is and explain why it's an outlier. What is it? What feature of it is it that makes it an outlier? What's the intercept? 72.95, right there. And what does that tell us? How would you interpret that? I like it. The predicted amount of time that it takes to finish the checkout when there are 0 customers in line in front of the selected customer is approximately 72.95 seconds. Yes, so a little over a minute. What's R squared? 73.33%. What does that tell us? (73.33% of the variation in time that it takes to check out, right, is because of what? Can be explained by the LSRL. Yes, the LSRL. So it can be explained by the linear relationship with customers in line. Which point? Oh, sorry. Yes. You can say either one. By the least squares regression line, relationship with, and then you still want to be very explicit in naming your X. I wouldn't just leave it as LSRL. Would that be enough to get credit? Maybe. The more explicit you are, the more precise you are with your communication, the greater the chance you're going to get full marks on that section. Which point up here would be the outlier? Where the X is about what and the Y is about what? X is about 3 and Y is pretty close to 0, right? It's certainly not up here at 250, which would still make it an outlier. But it's the Y is close to 0 and the X is 3. Why is that an outlier? It has the largest residual. It's not just that it has a large residual, because without that one, I could still pick out the point that has the largest residual, right? It doesn't follow the overall linear pattern. Based on the number of customers, the predicted time, or sorry, the actual time that it took to check out was way lower than predicted. Didn't follow the overall linear pattern there. All right, we've only got like 2 minutes until the bell rings, so I'm going to shut us down there. Tomorrow we will do Chapter 4. Chapter 4 was where we talked about the different types of studies and experiments. It's where we talked about cluster sampling and systematic sampling and simple random sampling, along with experiments, talking about explanatory variables and response variables, and random assignment.